This is a very topical issue and one that created a number of problems, last year for lakes throughout the state. And I do want to start off by thanking, again, our hosts and our sponsors. So tonight, I'm going to go through a lot of information. Some of you may have heard some of this before, but it definitely warrants repetition. But tonight, what I'd like to do is talk to you about what is a HAB, and more importantly, why do they occur? And even more importantly, what can we do to prevent and control these harmful algae blooms? So we'll get to the basics here. Harmful algae blooms. First off, this is nothing new for scientists. I'm a lake scientist. I've been studying lakes since the mid-'70s. And, we were aware of harmful algae blooms, although they were not called harmful algae blooms at that time. And so these have been studied for decades. But these problems have become more frequent and more intense. And it seems like the public and the policymakers, especially over the past decade, are starting to catch up to the science. So what are harmful algae blooms? It's essentially a bloom that's caused by cyanobacteria. And these organisms can produce high concentrations of cyanotoxins when they are in bloom form. And once we have a harmful algae bloom, we have impacts to the recreational uses of our lakes and ponds. It affects negatively the ecology of those water bodies, as well as the water quality of those water bodies. And the reason why we're coming together tonight is these high concentrations of cyanotoxins, when they are present in lakes and ponds, can impact the health of humans, pets, and livestock. So we need to sit up and pay attention to this and figure out what we can do to prevent and control these blooms. Now, cyanobacteria are very unique organisms. They are bacteria. So when you look at them from a cellular perspective, they're lumped in with the prokaryotes. So they're very much unlike normal algae or good algae. They're not eukaryotes, meaning that their cellular makeup is much different. They lack a membrane-encased organelles. They don't have mitochondria, but they can photosynthesize. So they share properties of both bacteria and algae. Other things that make them unique, first off, many of them, not all of them, but many of them can assimilate atmospheric nitrogen. They can actually pull nitrogen out of the atmosphere, and that provides them, therefore, with an unlimited source of nitrogen. Many of them are very biologically adept at assimilating organic phosphorus, and much more so than the good algae. And that's important. We'll get back to that a little bit later tonight. But the ability to assimilate organic phosphorus is very important. Finally, a lot of them, or an additional thing, is that many can regulate their position in the water column. And so on a cloudy day, like we had at the beginning of today, they can actually use these gas vacuoles to rise themselves up higher in the water column so they can be in really strong light and photosynthesize very well. There's other species of cyanobacteria that conversely do very well in very low light conditions. So they may actually bloom very deep in the water column, unbeknownst to us, and then a storm event may sweep those cells up to the surface, and all of a sudden we're in the middle of a really nasty water quality condition. A really cool thing about them that I find really interesting is the fact that even prolific filter feeders, like for instance, zebra mussel, will selectively reject these organisms. Some of it may have to do with size. Some of them have an oily or a waxy sort of coating. But some of it has to do with the toxins. And over time, even zooplankton and filter feeders have learned to reject these as a food source. But as I said before, one of the biggest things is that they produce cyanotoxins. So cyanotoxins are complicated organic compounds. The ones that we probably hear about the most in the news are microcystin and cylindrospermopsin. The ones that are of the greatest concern in freshwater environments are microcystin, cylindrospermopsin, anatoxin A, and saxitoxins. Anatoxin AS occurs in marine environments. I want to also stress that some of the harmful algae blooms that many of you may read about, the red tides down in Florida, those are caused by totally different species. Those are not cyanobacteria that cause those red tides. But in New Jersey, primarily we're concerned about the cyanotoxins, microcystin and cylindrospermopsin. And of those two, microcystin LR is probably the one you'll read about the most commonly. But I want to point out it's one of 60 different types of microcystin. So even for scientists, it's difficult to sort of like tease out what's going on and figure out where all of these compounds are coming from and what species are responsible for them. Now, cyanotoxins, you want to keep in mind, although they harm humans and pets and livestock, that's not why cyanobacteria evolved to produce cyanotoxins. They evolved producing cyanotoxins to really give them a competitive advantage over good algae. And so even when cyanobacteria cells are healthy, they'll be oozing out a little bit of these toxins, primarily to give them a competitive advantage. But when we really have to be concerned about, the amount of toxins in the water column is when the cyanobacteria die. When they're agitated, perhaps by like a large wind storm or a lot of wave action, or as a result of the application of an algicide like a copper sulfate treatment, those cells will break down, they'll essentially blow up, and they'll release cyanotoxins in very large quantities into the water column. And the problem there is that these compounds are very stable and they slowly biodegrade. So once they're in the water, they're there and it's difficult to remove them. The most common form of exposure is either through drinking water or recreating in waters that have been impacted by a bloom. Now, humans are pretty smart. We know when we see, water that looks a little bit funky and there's a scum on the surface, we shouldn't be drinking that water. But pets and livestock, not so much. But at the same time, we may look at a lake and it may look fine, but yet there's enough toxins in the water column to be a problem. And other times we may have a bloom and not pay any attention to that bloom, but that can create problems. And these toxins, basically, they manifest in three different ways. They can cause skin rashes, so they're a dermal toxin. They can affect the liver, and this is typically through drinking the water, so they're a hepatotoxin. And they can affect the central nervous system, and so they're also neurotoxins. Different species have different types of toxins associated with them, but typically cyanobacteria, the toxins that are produced, fall into these categories. As I said, livestock and pet mortalities, there's plenty of incidences of those types of events, and largely because of pets or livestock drinking contaminated water. And one thing we have to be careful with, particularly with dogs, they go swimming, they come out, they lick their fur, they ingest those cells break down, and the dogs get sick. And in some cases, dog deaths have occurred as a result of just dogs swimming in cyanobacteria contaminated water. There's also some data out there that show long-term exposure to high concentrations of cyanotoxins can be linked to various neurodegenerative diseases, such as Parkinson's, ALS, and Alzheimer's. The citation I've placed at the bottom of this slide is a very recent publication in an Australian journal talking about these linkages between these toxins and some of these neurodegenerative diseases. When we talk about cyanobacteria, as a scientist, I use the scientific names, and these are the genera that we're most commonly going to run into in New Jersey. Microcystis and Anabena are probably the two top cyanobacteria, particularly in the summer. Planktothrix, which used to be called Oscillatoria, is another species that creates a lot of problems in New Jersey. Phanozomenon, the picture that is in the center on the right-hand side, looks like little pieces of cut grass. That species prefers a little bit colder water, so a lot of lakes right now have a pretty good Phanozomenon colony going. And sometimes it will reach bloom densities even in the middle of the summer. And then Anacapsa is another species that we see particularly in the summer. Lingby and Gliotrichia are interesting because they're benthic forms. They actually grow down at the bottom of a lake or a pond, and then they'll surface once those mats reach critical mass. So the picture at the bottom right-hand side of the screen is a Lingbia bloom in a lake up in northern New Jersey that's really surrounded by pretty much nothing but forest. So these don't only happen in really what people would consider highly polluted lakes. These blooms actually happen in lakes that are in pretty good, pretty good condition, have pretty good water quality. I'm going to get just a little bit into how DEP defines a harmful algae bloom. I'm not going to spend a lot of time on this. I would encourage you to go to the DEP website and check out the information that DEP has put up online. I will tell you that it's very robust. And from a state, I deal with a lot of different states, and I would say New Jersey now is one of the leading states in terms of providing information for residents, doing research, conducting investigations, and monitoring HABs. So we're very lucky to have a very active DEP when it comes to HABs. Right now, DEP has just launched a brand new for 2020 mechanism or protocol rather to define HABs. They use a combination of cell counts with cell counts from 20,000 up to 80,000 with that ramping up to different levels of risk and severity of a bloom. And they also use toxin thresholds. And for microcystin, cylindro, spermopsin, and anatoxin, the respective concentrations of 3 micrograms per liter, 8 micrograms per liter, and 27 micrograms per liter. Now, DEP and scientists like myself also stress that even at concentrations, cell counts lower than 20,000 or toxin levels lower than, say, 3 micrograms per liter of microcystin, certain people may be a little bit more sensitive. Children, we know, are a little bit more sensitive. And people with compromised immune systems tend to be a little bit more sensitive. So they may have rashes or experience symptoms even without toxins being present or without toxins being at very high concentration. So just something to keep in mind. As I said, DEP has rolled out this new 5-tier action protocol. Dr. Fred Lubnow from Princeton Hydro and myself, on behalf of the Lake Hopatcong Foundation, the Lake Hopatcong Commission, Greenwood Lake Commission, and the Deal Lake Commission, we prepared a white paper over the winter, submitted that to DEP, requesting that they take a closer look at how they define and react to HABs. Unbeknownst to us, they were doing a lot of their own research at the same time. I'd like to take credit for a lot of this, but in all reality, DEP was doing a lot of homework on this over the winter as well. They gave us the courtesy to meet with us. We went over our points, and a couple of months ago, really about a month ago, they rolled out this 5-tier action protocol. And essentially the 5 tiers: watch, alert, advisory, warning, and danger. And if you look at this slide, you'll see that things ramp up as cell concentrations ramp up or as toxins become present in the water column. Again, I would advise you to go to the DEP HAB website. And I want to just stress that the advisory, warning, and danger risk levels where beach closures may occur. Now, keep in mind, DEP does not close beaches. That's up to the local and county health departments to do so. They only follow DEP these recommended risk levels. So hopefully, our local health departments and county health departments will understand some of these changes from last year. But these are the new 5-tier action protocols. If you go on their website, you'll find a slide like this, a lot more detail. What I've tried to do is cherry pick some of the most important information off of this slide. But go to their website and you'll get a lot more information about this new protocol. And there's also going to be new signage You'll see with these signs that'll be, again, issued by DEP to the health departments. As we ramp up from a watch to a danger level, there's different things, different types of activities, in-water activities or exposure, potential exposure, whether it's drinking or pets being in the water, and DEP will provide advice, either caution that there may be a problem or say, do not do this. Again, review those signs, review that on the DEP HAB website. I want to get back to the meat of the matter for tonight, and that's really why do HABs occur and what can we do to prevent them and either control them. So as I said before, this is nothing new. The public is becoming more aware thanks to state agencies and EPA. But we also see that there's an increase. Over the past decade, we're seeing more of these blooms occurring. They are becoming more intense and they're persisting for a longer amount of time. And the typical conditions really are what you would expect to see in the summer. Warm water temperatures, long days with plenty of sunlight for photosynthesis, and relatively stable water columns. And again, typical conditions is that you're going to see these blooms occurring in lakes that tend to have high phosphorus concentrations. And those are going to be the lakes that are subject to a lot of phosphorus loading, whether that phosphorus originates internally or externally. There's a lot of phosphorus that comes into these lakes, and as a result, in-lake concentrations of phosphorus are relatively high. So we have all of the makings for a bloom, whether it's a good algae bloom or it's a cyanobacteria bloom. But unfortunately, it's not as simple as it sounds. Typical conditions don't always lead to a bloom. Even in the middle of the summer, we may have lakes that never experience a cyanobacteria bloom. We also may have situations like we've seen in the winter where blooms occur and very high cyanotoxin concentrations are measured, even though environmental conditions are suboptimal. Another thing that we have to keep in mind, and this is why it's important to identify which cyanobacteria we have in our lakes, is that not all cyanobacteria cause HABs, not all cyanobacteria produce toxins, and even those that produce toxins may not produce large amounts, even during the bloom. So there's a lot of things that are going on in the background that we need to be aware of. One of the things that we are seeing, and it gets back to why we're seeing more frequent and intense blooms, seems to be climate change. And a lot of this seems to be, particularly in the Northeast, linked to warmer winters. We have earlier ice out or no ice formation on our lakes and an earlier onset of the growing season. And essentially what that means is that water columns warm up, light is able to penetrate deeper earlier in the spring, and we start to see these blooms manifesting earlier and earlier. And if the cyanobacteria can become dominant and outcompete the good algae, we may be in a situation very quickly where we have a HAB on our hands. In addition to that, we're getting more storms of increasing intensity. And with those storms comes additional phosphorus loading. Warmer summers may play a role, but not as big a role really as warmer winters. This is data that has been developed by Dr. Anthony Broccoli from Rutgers. And what's shown really on this slide is this warming trend in winter air temperatures, about 3.7 degrees Fahrenheit over the past 100 years, and 2.4 degrees Fahrenheit warmer over the past 100 years during the summer. The problem is really with these warmer winter water temperatures. So a lot of research is being done on that, but that seems to be part of the reason why we're seeing these more intense and frequent blooms. And then with that comes more rainfall. And what this slide, again, attributable to Dr. Broccoli, is what it's showing is the increase in extreme one-day precipitation events. So we're not talking about like the 100-year storm or the 50-year storm. We're talking about intense rainfall events that may amount to an inch and a half that are coming more frequently and during the summer. That creates a lot of problems because now we're washing in more phosphorus into our lakes. Last year, and probably one of the reasons why we had such bad HAB problems statewide, is that we had almost like the perfect storm type of conditions. We had a very warm winter, early ice out. This was in 2019, and an exceptionally wet winter and an exceptionally wet spring. So we had early growing season and a lot of phosphorus loading right at the beginning of the growing season. In addition, because of the wet winter and wet spring, we had saturated soils. That increased septic loading in those lake communities that are serviced by septic systems. And there was no place for stormwater to go. I mean, we couldn't infiltrate or we couldn't retain stormwater on site because the soils was saturated. So that resulted in more runoff. And then come July, what we started to see were these warmer air conditions. The water was warming up, and those warm, dry periods were then punctuated by these intermediate extreme rainfall events that brought in a lot of phosphorus at really the worst time of year, when HABs will typically form, and really stimulated a lot of those HAB blooms that we experienced in June and July of last year. Now, the common denominator to all of this is phosphorus, excessive phosphorus loading. The more phosphorus that we have in our lakes and ponds, the more productive they are. And that productivity is expressed in more organic carbon, and in lakes and ponds, that means more algae. So just like when you put more phosphorus on your lawn gets greener, you get more organic production in the way of grass growth. In lakes, the more phosphorus that enters, the more productivity, and that gets expressed either as algae or as cyanobacteria. So how much is too much? Well, it doesn't take a lot. The limiting nutrient in New Jersey is phosphorus, meaning that the more we add, the more productivity we have. And you only need about 0.04 milligrams per liter to stimulate a bloom. The state water quality standard for phosphorus in lakes is 0.05 milligrams per liter. So you can actually be below the state water quality standard, but yet have more than enough phosphorus in your lake to stimulate a bloom. And most lakes in New Jersey are eutrophic. They are phosphorus rich. It only takes a pound of phosphorus to create 1,000 pounds of algae. So bottom line, we're talking about phosphorus concentrations in the parts per million, 0.04 parts per million or milligrams per liter, in very small amounts of algae to create, very small amounts of phosphorus rather, to create a lot of algal biomass. Now, one thing that you've probably heard me say before, or that I like to stress, is that just because a lake is experiencing a HAB or an algae bloom does not mean that it's dead. It's just the opposite. It is a water body that really needs to go on a diet. It is just nutrient rich, and as a result of that, unlike us, where we eat a little bit too much and we start to develop a spare tire, in lakes, what ends up happening is that you get too much phosphorus, and that phosphorus ends up stimulating too much in-lake productivity. And that means making that lake more likely to experience a HAB. Now, most of the lakes in New Jersey, as I said, are eutrophic, which doesn't make them dead. That doesn't mean that they're bad, but it does mean that they have to be managed, because if they're not managed and managed properly, they're going to experience an algae bloom, or in worst case situations, a cyanobacteria harmful algae bloom. So here's eutrophic Lake A. This lake, I've studied this lake. It's up in Morris County. Phosphorus concentrations typically range from about 0.04 to 0.07 milligrams per liter. Doesn't look too bad. And for the most part, it is a lake that, although eutrophic, has pretty good water quality. Here's another lake in New Jersey that is eutrophic. Phosphorus concentrations here are not that much different than Lake A, usually up around 0.07, 0.08. But this is not what you want to see in your lake. This is a pretty intense Anabaena bloom that's occurring in that water body. So the bottom line is that we know phosphorus is the problem. And we know that when we have too much phosphorus entering our lakes, that we're going to have these blooms. And so what do? How can we monitor the conditions that are responsible for a HAB, and how do we monitor a HAB and track these cyanotoxin problems that are a result of a HAB? Well, my mantra as a lake manager has always been, don't treat the symptom and don't react to the symptom. You need to take the time to identify and correct the cause. And I've used this analogy in the past. All of us at some point in time has had a fever. And a fever is just a symptom of you being sick. And that illness could be a number of things. It could be a pretty bad infection. It could be common cold. The treatment that you would take, the medicine that you would take to make you better is going to be different in both those situations, even though in both situations you're experiencing a high fever. And that's the same thing with lakes. Algae blooms and HABs, is a function of phosphorus loading, but there's a lot of other things that happen. But if we don't take the time to figure out what is causing the problem, and all we do is react to the bloom, and then say, okay, we're going to treat it with an algaecide, we're going to get rid of that bloom. We're maintaining the lake perhaps, but we're not managing the lake. And what we want to do to control HABs and prevent HABs is actually manage our lakes and manage them effectively. Now, although phosphorus is the primary root cause problem, there's a lot of other things that go on with lakes. They're very complex living organisms. There's a lot of different types of interactions that are occurring between the biology, the physical attributes of the water body, the chemistry of that water body, and particularly the hydrology that will determine whether or not a bloom occurs. So it's very important that we take the time to understand those interactions in order to figure out why we're experiencing a HAB, and even more importantly, what can we do to control eutrophication and prevent a HAB from occurring. So just like you wouldn't go out and build a house without a plan, you can't expect to manage a lake and manage HABs without having a technically sound management plan. And a technically sound management plan requires a collection of data. So proactive lake management is the most effective way of reducing the threat of a HAB, but it does involve a lot of work. Number one, you need to identify all of your sources and quantities of phosphorus entering the lake. We need to know where all of that phosphorus is coming from. Is it internal? Is it external? Is it septic systems? Is it stormwater? Is it geese? So it takes time to identify and quantify all of those sources. And secondly, as I said before, because lakes are very complicated living organisms, we need to take the time to collect the data that allows us to understand the ecological dynamics of that water body. And what is it about that water body? What are the perfect storm type of conditions that come together that allow a HAB to occur and be sustained? So out of these watershed and lake management plans that I've developed, a part of that is my HAB management action plan. And I sort of break this down into three different areas of action. There's the root cause element, and that's really where I'm looking to decrease external phosphorus loading and prevent HABs. For the most part, watershed-related loading is where the majority of the phosphorus that enters a lake, that's where it originates. So we need to understand that root cause and take a look at what we can do within our watershed. There's other in-lake measures that can be done proactively to decrease internal phosphorus loading, which is another cause of HABs, oftentimes secondary cause, but it's important to understand what's happening within the lake and what kind of in-lake measures we can implement. And I want to talk on all three of these towards the end of this presentation. And then we have reactive management measures, and this is when you have a bloom and the things that you can do to lessen the severity or the duration of that HAB. So, again, root cause, figure out where all the phosphorus is coming from, and what do we do to prevent that. Proactive in-lake management measures, what can we do to decrease internal loading and prevent HABs from manifesting. And then reactive management measures, things that we do to lessen the severity of a HAB. So I'm going to focus really on the root cause watershed management action measures. A few years ago, I developed a strategy called PAIR, Predict, Analyze, React, and Educate. It's all based on the collection of data. If you want more information, you can email me. I'll be more than happy to send you more information on PAIR. But essentially, it really focuses on collecting certain specific types of data and then using that data to first forecast when a bloom may occur, use that same data to analyze how bad my bloom may be and what type of things I should be doing to address that bloom. And also you can use that data to evaluate, if you are implementing measures, how successful have those measures been. And that gets into our React element. We can also use the data to educate the community about HABs, about the actions that are being taken to prevent HABs, and what they themselves can be doing to prevent HABs. A lot of people ask me, what should I be collecting? Okay, so the keystone parameters that are used to predict or analyze a cyanobacteria problem first begins with what's called in-situ measurements. These are measurements collected of right in the water column. You get immediate feedback using meters of dissolved oxygen, temperature, and pH and profile from surface to bottom, and the clarity of the lake, the Secchi clarity. You need to measure the amount of nutrients, phosphorus and nitrogen, how much is present in the water column. Chlorophyll A, which is the photosynthetic pigment that's shared by cyanobacteria and various algae, should be measured. And then we also want to know which types of plankton are in the water column, the good algae, the phytoplankton, as well as the cyanobacteria, what species and how much. And then if we have the opportunity, actually measure the types of toxins that are present in the water column, primarily microcystin, but cylindrospermopsin if we can as well. These are sort of the threshold values that I've come up with for forecasting a HAB. This is not in the middle of a HAB, but when it looks like there is conditions of an impending bloom. Once our clarity sets to dip below a meter, or about 3 feet. Our chlorophyll concentrations exceed 20 micrograms per liter. Our plankton cell counts are dominated by cyanobacteria, and we're seeing cell counts in excess of 10,000 cells per ml. Some of the cyanobacteria produce taste and odor compounds, MIB and geosmin. Those products can be measured, and once we see them above 10 nanograms per liter, we know we have an impending bloom. Some of this data can also be collected using field kits, fluorometers, and phycocyanin meters that enable us to forecast a bloom. And then you can actually go out and measure the concentrations of cyanotoxins, either using these simple-to-use field kits or collect samples and send them off to a lab, like Garden State Labs, who now does cyanotoxin testing. I like the field kits. It's sort of like the canary in the coal mine. The data may not be, absolutely positively the greatest, but it does provide you with reasonably accurate results, and particularly in that range from 0 to 5 micrograms per liter. And there's a lot of value in 0. So if you're collecting data and it's 0, 0, 0, there's no toxins in your water body. So that's good. The thing is, these are relatively cheap to run. They're really quick in terms of getting turnaround. And if you have enough data, you can link it to cell count data, chlorophyll data, et cetera, to provide you with a more robust database. And if you do have the opportunity to collect samples and send them off to a lab, then you can get some very accurate concentrations of how much of these various toxins are present in your water column. DEP does this type of testing on a lot of the public lakes. And as I said, Garden State Lab now provides that service for private as well as public lakes. These field fluorometers are a little bit pricey. They may go about like $5,000 or so, but DEP does recommend their use. They are used by DEP and by a number of health agencies. but they do give you a quick and relatively inexpensive way to track in-lake cyanobacteria data. So it's a really good way of figuring out if you have a cyanobacteria problem without having to go through a lot of the sample collection and lab analyses. So that just gives you a quick and dirty overview of the types of data that need to be collected and how that data will put you in a position to forecast the bloom and then tell you how bad of a bloom you may be experiencing. And as I said before, also figuring out how good a job the mechanisms or the techniques and different types of measures that you've put in place is doing either to prevent a HAB or to decrease the severity of a HAB. Well, let's talk about preventing and mitigating HABs. We know that phosphorus is the bad guy here. And if phosphorus is the food that's responsible for all of these blooms, where is this all coming from? Well, this is where collecting data is important, because we'll see that some of this phosphorus loading may originate internally from within the lake itself, released from the sediments, but a lot of it comes from external sources. As I said before, septic, stormwater, geese. So there's a lot of different external sources. And the amount of phosphorus and the amount that's coming from each of those sources is going to vary seasonally. So it's important that we collect data over time and we collect the correct type of data to figure out how much of this phosphorus is coming in and where is it all coming from. So I said there's three primary sources of phosphorus loading when we break things down. There's internal, and I'm going to get into this in a little bit more detail in a minute, but this results from thermal stratification. When the water column stratifies and the bottom of the lake becomes anoxic, that changes the bottom water chemistry, or the bottom sediment chemistry rather, and as a result you get a lot of influx of phosphorus from the sediment. This is internal, and I like to refer to it as sort of like a hidden source. A lot of people don't pay attention to that particular source. Lake communities that are serviced by septic systems, that can be a major source. Any home within 300 feet of a lake shore is a potential source of phosphorus to that lake. And the intensity and the amount of phosphorus loading from septic systems increases with the age of those septic systems, the density of development, shallowness to bedrock, and the shallowness to groundwater. So those of you that live around lakes, think about, how and when your lake community was developed, the density of that development. And a lot of lake communities are on pretty steep, shorelines with shallow depth of bedrock and shallow groundwater. So all the perfect conditions for septic loading. But stormwater tends to be the universal source of phosphorus loading, and typically for all the lakes in New Jersey, the most significant source of phosphorus loading. Fortunately, it's also perhaps the easiest source to manage and reduce. There's things that we can do ourselves on our individual lots and things that can be done on a community basis to decrease stormwater-related phosphorus loading. North American Lake Management Society, I was past president of NOMS, had a great tagline back in 2008 that a lake is a reflection of its watershed, meaning that if you see a problem in a lake, you can probably turn around and look at the watershed and get a pretty good idea of why those problems are occurring. And most of it's because of land development and improper or inadequate stormwater management. Stormwater runoff, we're the enemy. Definitely, we create a lot of our own problems with phosphorus loading that leads to HABs. For the lakes that I've studied, and I've studied probably close to 300 or more, really the majority of those lakes, about 80% of them, stormwater was the primary source of phosphorus loading and became the foundation of the HAB management plan. What do we do about managing stormwater entering our lake? So anything that can be done to reduce the amount of phosphorus by controlling the amount of runoff becomes part of our root cause approach to controlling eutrophication problems and harmful algae bloom problems. That stormwater connection is pretty intense. It directly affects the amount and the timing of phosphorus loading. Again, reflect back to 2019 and the storms that we had in July and how those triggered some of the really nasty blooms that we saw in the middle of the summer. Indirectly, it can affect the thermal properties of our lake. When we get a lot of rainfall, it causes the surface of the water to cool off a little bit. Cooler water is less dense, is denser rather than warmer water, and that water sinks, causing the water column to become unstable and mix. It can be a source of legacy loading in terms of all of the phosphorus that's bound to sediment that enters our lake, gets stored in the lake, and then gets released through internal processes. And indirectly, as I mentioned before, when we have saturated soils, it can have an indirect effect on septic loading, causing more septic to run horizontally with that groundwater into our lake, as opposed to that septic wastewater percolating vertically down through the soil horizon. So successful lake management and HAB prevention control must involve some type of systematic stormwater management that emphasizes phosphorus load reduction. It sounds like a broken record, but that is key to controlling and preventing HABs. Stormwater management strategies, you can start right, with source control, meaning don't allow that much phosphorus to enter our systems in the first place. Non-phosphorus fertilizers are required by law in New Jersey since 2012. So make sure that you're using a non-phosphorus fertilizer, or if you have landscapers that they're using non-phosphorus fertilizer. You can look at alternative lawn covers that promote more retention of runoff. Waterfowl, particularly geese, are a big problem. 4 geese produce as much phosphorus in one day as 1 septic system. So I'll repeat that. 4 geese equals 1 septic system in terms of phosphorus loading. So don't create conditions and don't promote conditions for geese to colonize your lake or pond area. And then what we want to do is find ways to intercept and hold on to stormwater, keep that on site as much as possible, let it percolate down into the soil as opposed to running off. The more it runs off, the more transport of phosphorus you end up with, and that phosphorus eventually gets deposited in our lakes. We can also look at delivery control techniques, and this is where we're actually intercepting and treating stormwater runoff. And this can be done, as I mentioned before, on our own individual lots using best management practices, BMPs, as well as in larger scale on a community basis or even a regional basis, using the types of best management practices that are being implemented now at Lake Hopatcong, Greenwood Lake, Deal Lake, and numerous other lakes throughout the entire state. The bottom line with stormwater management when it comes to lake management is that we want to decrease the volume of runoff, turn down that volume. And green infrastructure provides a perfect way of doing that. So that's another new term in stormwater management, using these naturalized type of techniques to intercept and hold runoff on site and decrease the volume. The less volume, the slower the flow rates, the less quantity of runoff, and that means the less pollutants that are being discharged into our lake. The less nutrients means the less opportunity for a HAB. So, as I mentioned, green infrastructure, this is a very adaptable term. Some of you are probably familiar with it. It does cover a wide variety of different types of products and technologies. But essentially what we're trying to do is mimic nature by soaking up and storing water and using vegetation, soil, and other natural processes to treat, infiltrate, and then evapotranspire runoff. The less runoff, the less pollutant loading, the less opportunity for a HAB. There's a lot of really simple and effective ways that this can be done in lake communities. Rain barrels, rain gardens, we're all familiar with that. This can be done to either retrofit existing infrastructure. These can be scaled from things that can be done on your own lot to, as I mentioned before, community systems or regional systems. And they can even be integrated into very tight spaces. So there's a lot of different types of opportunities here. Again, we're pretty much blessed with the fact that we have Rutgers and we have Chris Abrupta, who has been promoting green infrastructure and providing opportunities statewide, not only in lake communities, but in every community, to manage stormwater using these green infrastructure techniques. So again, hats off to Rutgers and Dr. Abrupta. And on this slide, I provide a link to the Green Infrastructure Guidance Manual that has been developed by Rutgers. These are just some examples of what I call these pocket best management practices. Again, these little rain gardens. If you live in a lake community, having a buffer along the edge of your lake to intercept runoff. Maybe if you're in South Jersey or we have amenable soils, creating infiltration opportunities by collecting downspout, a discharge and putting that down into the ground using these little infiltration basins, and then the rain gardens themselves, which help collect and manage rooftop runoff. We can also do things around our properties or around community properties to disconnect impervious from pervious areas, and basically, again, use vegetation to collect some of that runoff that's coming from paved surfaces or rooftops, run that into some of these vegetated solutions, and allow that water to be soaked up and those pollutants to be removed either by the soil or by vegetation. And then there's a variety of these community-based solutions and actions that can be taken throughout a lake community that involve bioretention basins, bioretention swales, and the like. These are some infrastructure retrofits that are being conducted around Greenwood Lake, and basically taking existing developed areas and again, taking some of that runoff that would come from those impervious surfaces and routing them now into these green areas where we're controlling that runoff, keeping it on site longer, and removing pollutants. So those are all things that can be done that are part of our stormwater management initiatives, which as I said, are the most important things that can be done in terms of preventing HABs. Controlling the amount of runoff, decreasing the amount of runoff, decreasing the amount of pollutants that are leaving our properties. And by doing so, that decreases the amount of phosphorus entering our lakes and ponds and decreases the opportunity for HABs to manifest. Now, there are other things that we can do within our lakes. I've listed here some of the more common types of in-lake measures. Again, these are primarily designed to either reduce the amount of available phosphorus or to alter conditions within the lake that decrease the opportunity for a bloom to actually occur. These take a lot of information gathering and a lot of data to determine what works best in your water body. But they can be utilized, and probably the two proactive in-lake measures that are utilized most commonly are aeration and nutrient inactivation. So with aeration, what we're trying to do is keep the water column mixed and maintain enough dissolved oxygen at the bottom of our lake to prevent that internal phosphorus loading. And I'll get into that in a second. With nutrient inactivation, what we're doing is we're applying a product that binds with phosphates, the phosphorus that is most easily assimilated by algae, thereby preventing or decreasing rather the amount of food that's available for the uptake by cyanobacteria. At very high concentrations, these same products can be utilized to actually strip the water column. But we tend to want to use them more in the standpoint of binding available phosphates and decreasing the amount of food available for bioassimilation. So I'll just touch very briefly on these techniques. I'll put a little bit of a plug here. Those of you that want to learn more about this, in about 2 weeks, actually about a month, I'm going to be teaching a 2-day pond course through Rutgers Continuing Ed, and later on in September, a 4-day online course, again through Rutgers Continuing Ed, on lake management. So you can check that out on the Rutgers website, the Office of Continuing Education. But bottom line is, if you want to learn more about this, I'll be more than happy to share more information with you. But thermal stratification and HABs. All of you are familiar with this. In the summer, you dive into a lake, it's very warm at the surface, and all of a sudden it gets very cold. Well, there's different layers, and those layers set up because of temperature, but as water warms, it becomes less dense. And so what ends up happening is you have this warmer, less dense water sitting up at the surface and cooler, denser water down at the bottom. If you've got enough of a density difference that occurs, what can end up happening, and this only needs to be about 2 to 3 degrees centigrade difference, you get enough of this layering to create stratification. And that stratification creates a thermocline, and when that thermocline becomes established, the bottom waters can no longer mix up to the surface, and as a result of that, you end up with oxygen being depleted at the bottom of your water body. Now, this happens not only in deep lakes, but it can happen in any water body that's as shallow as 8 feet deep. So it's very, very common even in lakes that are relatively shallow. Once we end up with no oxygen down at the bottom, even if it's for a short period of time, the sediment chemistry changes, phosphates become released from the water column into the water column from the sediment, and that regenerated phosphorus can stimulate or support a HAB. And as I mentioned, this doesn't happen just in deep lakes. It can happen in lakes that are as little or as shallow as 8 feet deep. So you end up with no oxygen down at the bottom, these anoxic conditions that are occurring below your thermocline, and you get a large release of sediment-bound phosphorus, metals, and minerals up into the water column. But we're mostly concerned about that phosphorus, and that liberated phosphorus, this internal phosphorus load, can stimulate and sustain a bloom. So aeration can be utilized to address this by keeping the water column mixed and maintaining really good oxygen levels down at the bottom of our lake. There's a lot of different types of aeration techniques that are out there. The most commonly implemented in New Jersey are called destratification techniques that keep the water column vertically mixed throughout the entire summer. As I mentioned, nutrient inactivation is another technique that's utilized to control internal phosphorus loading. The products that you see most commonly utilized are alum, polyaluminum chloride, and Phoslock. Those products are typically applied in low concentrations to bind phosphates, but alum and PAC can also be applied at very high concentrations to strip the water column and remove all particulate material, including algal cells. Alum is the most commonly utilized nutrient inactivant. As it's applied, you'll see that the water column turns like this milky color. That's the flock. As the flock settles through the water column over the matter of hours, it binds all the available phosphates. And if that application is done at a really high concentration, it'll physically strip the water column and clarify it. There's also metered dosing systems. Those of you may be familiar with the systems that I designed for Lake Mohawk and White Meadow Lake that actually pulse in small amounts of alum over the course of each day to bind phosphates and thus decrease that internal load of phosphorus and thus do away or decrease the opportunity for algae blooms and for HABs. Okay, so those really cover the techniques that you would implement to prevent HABs, whether by controlling your external loading, which, as I said, is the most important thing. That's stormwater management has to be emphasized as the most important thing to do. And then the things that can be done to control your internal loading. I haven't talked about septics. Septics are a little bit more difficult to manage. Typically right now, what we can do is do good septic management, keep our septic tanks pumped, make sure that they're operating correctly, keep our leach fields operating properly by not getting them saturated. So that means keeping stormwater off of those leach fields, watching what we plant on them, and making sure that our septic systems are running properly. But septic management can be a little bit difficult. But what do I do if I do have a bloom? Well, the most common thing that's done is to go out and do an algicide treatment. And the most commonly used algicide is copper sulfate or some other type of copper product. And yeah, it will do a pretty good job initially of killing off the algae, but as I'll show you, it's not always the best approach. There are other non-copper algicides that are out there. They're a little bit more expensive. They actually oxidize or break down the cells using a different type of product that's more like a peroxide. And then there's filtration techniques as well. But most commonly, people go out, and if they have a bloom, they implement an algicide treatment. So what's so bad about just bombing our lakes and ponds with copper sulfate? Well, the problem is that when you use copper, although it can be part of your solution, it shouldn't be the go-to solution. What ends up happening is that when copper sulfate, how it works is it causes the cell walls to blow up. And when the cell walls blow up, we release all of these cyanotoxins, very high concentrations, very quickly. In addition, it releases a lot of organic phosphorus. And as I mentioned before, cyanobacteria are extremely efficient at using organic phosphorus as a means of growing and photosynthesizing. So when we rely heavily on copper sulfate, yes, we may knock down the bloom for a short period of time, but now we've released a whole bunch of cyanotoxins into the water column, and we've released a whole bunch of organic phosphorus into the water column. So what have we done? We've created a condition that's that much more conducive for more cyanobacteria growth. So it can be like the dog chasing its proverbial tail. So although it can be part of your strategy, it shouldn't be the only thing that you're doing, and it should not be your go-to solution. Your go-to solution should be decreasing the amount of phosphorus that's entering the lake in the first place, which means good stormwater management. So as I said, you'll get a temporary fix, but it really is not the salvation for your lake. And also, I want to just emphasize a little bit here with this increased public awareness of HABs. I've seen a lot of this voodoo science, these snake oil type of remedies, silver bullet remedies. Keep in mind that nutrient management is the key to preventing HABs. You need to understand what causes the HABs, the cause and effect relationship, etc. So if you see some of these things that are being advertised as easy fixes, especially if they lack any type of scientific collaboration or corroboration, run away. It's basically voodoo science. And it's, these are the things that you don't want to be investing a lot of time and money in. So in summary, I've gone through a lot tonight. I understand, as a limnologist, I deal with this on a day-to-day basis, but this is new to a lot of you. So just, to summarize, HABs are not anything new, but we are seeing an increase in the frequency and severity of those HABs. And I think a lot of that does have to do with climate change, and a lot of it has to do with more storms and the intensity of those storms. We do know that HABs create significant problems that affects the health of humans, pets, and livestock. New Jersey lakes, unfortunately, are phosphorus rich. Therefore, they're susceptible to HABs. So what we need to do, again, broken record, I can't beat this horse more, but we have to decrease phosphorus loading. And because most of that loading is associated with stormwater runoff, stormwater management becomes a key part of your HAB management strategy. Green infrastructure provides a great opportunity for decreasing phosphorus loading and managing runoff. This can be done on an individual lot basis, and then it can also be scaled up for our communities and even at a regional level. So our goal is not to see signs like this. We want to do away with that. We want to have our lakes and ponds swimmable, fishable, and enjoyable. So with that, I'll leave you with a couple of closing slides that have sources for more information, either from DEP, North American Lake Management Society, or New York State DEC, EPA, and some other sources. And those of you that do have pets and have concerns about pets, pay attention to these 3 different links. There's some very good information here about how to protect your dogs, from HABs and problems associated with HABs. So with that, I say thank you, and I think I will turn it over now to Elliot and to Zach.
Yes, thank you, Steve. Thank you for sharing your incredibly deep knowledge about HABs in ways that we can understand and digest. And I'll be moderating the question and answer portion of this. We have plenty of time. We have about 45 minutes. Before we move over to the questions, and as they come in, I'd like to launch a quick poll for those of you who are watching from the Zoom platform while these questions are being asked. If you can take a moment to answer this, it'd be much appreciated. I have a question, Steve, to start as we wait for the questions to come in. So we are 9 days from the beginning of summer, 22 days from 4th of July weekend when things got really crazy last year. Are there any indications that you can tell today that can predict what we might be facing this summer in northern New Jersey and the Highlands with our lakes?
Yeah, I think maybe the good news is that things are shaping up right now not as bad as they were shaping up last spring. We did have, once again, a very warm winter. Most of our lakes did not experience much in any way of ice cover. So the growing season definitely started earlier. We've had some pretty good amount of rain this past month and a half or so, but not as bad as, not as wet a winter or as wet a spring as we experienced in 2019. With that said, I do get data from given lakes and reservoirs in the state, and we are seeing already, some increases in cyanobacteria numbers, but they're still pretty low. So I'd say right now we're about where I would expect us to be during a typical year. I'm not right at this point in time expecting things to go haywire, but nature is nature. It doesn't take a lot for a HAB to manifest. So right now we seem to be in a pretty good place, but I would still be cautious.
Okay. Well, some questions are coming in, some simple ones. Does copper sulfate negatively affect good flora and fauna in a lake?
Yeah, that's something that you really have to be careful with. So number one, copper sulfate is an algicide, and it will kill the good algae as well as the cyanobacteria. And really what we want to have in our lakes is a healthy algal community that's composed of the good algae. So unfortunately, when you kill off algae using copper sulfate, you're killing off the good algae. In addition, zooplankton, which are the base of the food chain for a lot of our fish, are 10 times more affected by copper sulfate than the algae is. So the residual effect is longer term, and certain fish, for instance, trout, can be sensitive to copper. So although we don't see a lot of fish kills as a result of copper treatments, that's something that you have to be aware of, that it could affect fish life as well. But my biggest concern with copper treatments is that you are killing off the good algae and you're creating these conditions that are that much more, I would say, that facilitate more cyanobacteria blooms.
Okay. You mentioned field measuring kits. You know where someone can acquire them? Field fluorometers.
Yeah, the fluorometers, for instance, there's a number of, you can basically, I would suggest just go online and, Google fluorometer, field fluorometers. I'm not going to promote a particular brand, but I will say that In-Situ, the company called In-Situ, IN-SITU, makes a really good field fluorimeter. But there's a number of really good field fluorimeters that are out there, and you can probably get those from forestry supplies and other online companies like that.
Okay. Someone asks, as these HABs have become increasingly severe over the last few years, have lakeside communities that you've noticed increasingly become interested in looking at stormwater runoff management strategies that they can locally implement to address the problem, as opposed to fixing the problem once it's occurring in any particular summer?
Oh yeah, definitely. I mean, there's more and more lake communities that are, for instance, taking advantage of Chris Abrupta and Rutgers, and they are doing rain garden community demonstrations, rain barrels, and things like that, obtaining grants from DEP for implementation of stormwater measures. And actually, like for instance, Culver Lake has just entered into a public-private partnership with Franklin to actually do some stormwater management around Culver Lake, starting with some small basin inserts, and hopefully, that'll become some larger, more involved projects. But those types of things are happening around Lake Hopatcong, Greenwood Lake, Lake Mohawk. There's plenty of examples like that statewide.
Right. Yeah, I understand it's the Walk Hill River Management Group that has been very proactive up in the Culver Lake area, installing green infrastructure. And there's been a lot of interest to do that.
Yeah, absolutely. And even like, for instance, Deal Lake, right there in Asbury Park, the middle of a very highly urbanized, area, they're implementing a number of green infrastructure stormwater projects. I got them a grant a few years back. They did a number of stormwater, green infrastructure stormwater projects. They just obtained another grant where they're doing some more green infrastructure stormwater projects. So it's not just, suburban lake communities or rural lake communities that can take advantage of this. Even in these highly developed areas, there's opportunity to do green infrastructure and retrofit some of our existing stormwater collection and treatment techniques, or treatment systems rather, and implement these techniques where, they haven't been used in the past.
Yeah, and there is grant funding available, and the expertise of Rutgers Water Resource Management Department to implement them. So that's great. Another question is, can poorly maintained septic systems contribute to HABs, even in the absence of heavy rains and saturated soils?
Yeah, absolutely. I mean, I've modeled this, and I've seen this in plenty of lake communities. The interesting thing is that you can have a septic system that does a great job at removing bacteria. So from the standpoint of meeting code with respect to bacteria removal, doing a fine job. But there's only so many binding sites within your septic field for phosphates. And as that septic field ages, the ability to bind phosphorus drops off. And if you've got these compromised conditions where you've got shallow depth of bedrock, shallow depth of groundwater, small lots, and you've got larger homes that are being built on those lots, more impervious cover, that can all start to compromise the ability of that septic system to remove phosphorus. So although it may not constitute a health problem from the standpoint of bacterial loading, you're still getting a fair amount of phosphorus loading and nitrogen loading into that lake system.
Why do you think there isn't more septic management being responsibly taken care of? That it is a problem in so many lake communities. I mean, a septic system is something that's supposed to be maintained. There are schedules for maintenance. Why is it such a problem?
Yeah, I think a lot of lake communities now do have mandated pump out schedules and inspection schedules.
Right.
The New Jersey code has changed over the past few years to allow for these advanced wastewater treatment techniques that have a higher efficiency of removing phosphorus and nitrogen from the wastewater stream. Again, at Culver Lake, there's some experimentation being done right now with a system that injects small amounts of alum into the wastewater stream before the wastewater reaches the septic tank. So now you're removing phosphorus. You're allowing that bound phosphorus to settle out with the alum in the septic tank, and that phosphorus doesn't reach the lake. So these are things that are becoming. I think they're being used more frequently. But in the old days, it was you had a camp or you had a summer cottage. People went up. They didn't use it. Other than about 3 months out of the year. Now they're being turned into full-time homes, and some of those septic systems are old, and they need to be renovated. But it costs a lot of money. A typical septic system, $20,000, $30,000 to bring up to code. And there's no grants out for that. So I think that's one of the reasons where you don't see a lot of emphasis being placed on septic management.
Someone poses an interesting question about septic maintenance on limestone bedrock. Is limestone bedrock a source in itself of phosphorus?
Not that I'm aware of. I can see where you may end up with more, like a greater amount of groundwater loading, and maybe in those types of situations. But it could be, but that's something that I'm not aware of. So I don't know.
Okay. I asked it, the question was asked, and we have lots of limestone in the highlands.
Oh, yeah.
Many lakes treat early with alum and PAC. What is the risk they wipe out good algae and set the plate for cyanobacteria?
Okay, so I think there might be a little bit of confusion there because alum and PAC are not algicides. They don't kill algae. What they do is they bind phosphates, okay? So you're removing phosphorus from the water column. So there might be a little bit of confusion there. Nutrient inactivants, alum and PAC, are not algicides. They have no algicidal property other than the fact that they do absorb and reduce the amount of phosphorus that is needed by algae to grow. So I don't think that there may just be a little bit of a confusion there with those types of products.
Okay. If an aeration system is used where they are first placed in the lake, how do you determine the size or the number of aerators that would be effective?
Yeah, you need a fair amount of data on that. This is where a lake is not the case. It's going to be a function of the depth, the shape, and size of that water body, and where how much of a thermocline that's actually forming, and how much of that anoxic hypolimnion, that deep water that becomes devoid of oxygen. How much of that volume constitutes the entire volume of the lake? There's a lot that goes into it. There's various equations that are used to figure out what the oxygen demand is, and that can be utilized then to properly size an aeration system. But it takes a lot of work to figure out exactly what to do and how to do it correctly.
And what the right combination of strategies are, I suppose.
Correct. Right. Whether you're going to de-stratify the lake column or you're going to maintain it stratified and just put, maximize reoxygenation of that deep layer in the lake. There's a lot that goes into it. There really is.
Well, here's not a question, but an offer of help, which is very encouraging to hear. An environmental science student at Rutgers University in Newark asks, what can students do to contribute to helping this? Are there organizations that are recruiting students for internships or volunteers to help collect data?
Yeah, as far as like data excuse me, data collection. The only thing that I'm familiar with that's citizen-based right now is the CLONET program that is being implemented through Monmouth University and Dr. Jason Adolph. It's science-based, monitoring, and he goes through tests. He trains volunteers and provides them with test kits, etc. If students want to learn more about what they can be doing, I would advocate strongly that they become members of the North American Lake Management Society. NALMS is it is a terrific hands-on opportunity for students to interface with the leading limnologists, not only in the country, but throughout the entire world. And New Jersey Coalition of Lake Associations, in the spring and fall, have meetings at Lake Mohawk. Obviously, that's not happening now, but New Jersey Cola is another great source or another great way for students to get involved with lake management, right at the ground level.
Yeah, NJ Cola is a member of the coalition, by the way, New Jersey Highlands Coalition. And perhaps this Rutgers student should find out if there's any opportunities with the Rutgers Water Resource Center with Chris Abrupta.
Right, also NJIT, has a program as well. I know they're doing a lot with green infrastructure, stormwater management. They're going to be implementing a project at Deal Lake, with actually harvesting HABs. So NJIT is another, place to go to for students to perhaps become more involved with HAB research and things that can be done or things that are being done to study HABs statewide.
Okay, well, I've been told that this is the last question, and you're probably exhausted, Steve, after that very great presentation and now answering questions. How can private lakes pressure their townships or municipalities to perform work on improving stormwater runoff and adhere to their stormwater management plans? And how have lake communities responded to the idea of better septic and stormwater runoff management, which could be quite costly?
Yeah, well, that's a really good question. And, what I tell most lake communities is that there is a basis for doing that. First off, lakefront properties pay higher amount of taxes than non-lakefront properties. So, I think number one, they're making a contribution to the town and to the town revenue coffers. But MS4 is the stormwater permitting process in the state that towns are supposed to be implementing. And through MS4, I feel that there's a lot of opportunity for communities, lake communities, to deal with their townships or towns or cities, to ask them as part of their MS4 compliance to do more in the way of green stormwater infrastructure implementation, to retrofit existing stormwater collection systems, and for lakes that have documented HAB problems or have documented phosphorus problems where the phosphorus concentrations exceed the state standard. I think that also provides the opportunity to go to these towns and say, you have the responsibility through MS4 to be improving stormwater, the quality of stormwater throughout the entire municipality. And you can use some of that effort with our lake community. We're paying taxes, we're paying a lot of taxes. And, that might be a vehicle, but I would say MS4 is, and that MS4 permit to me is probably one of the best vehicles by which to push. And then of course, stormwater utilities, trying to get towns to implement stormwater utilities, and that which would provide them with the resources to properly manage stormwater runoff, and then have the resources in place to maintain and care for the measures that are put in place to better manage that stormwater runoff.
Right. And MS4 permits is the municipal compliance with the state regulations for municipal implementation of stormwater policies. So every municipality must have an MS4 permit, and that's how they're implemented on the local level, and people can be ensure that they're being compliant. And the stormwater utilities, something that the New Jersey Highlands Coalition and our partner organizations promote as an equitable way to raise money to deal with stormwater management on a local level. I mean, the state can help out to some degree, perhaps the county, but there's a lot of land use issues that have to be addressed, and those are local decisions and locally implemented, and that could happen through a stormwater utility.
Yeah, absolutely. And the thing is, even something as simple as upgrading the grates on catch basins to decrease the amount of floatables and to decrease the amount of particulate material that is discharged into a lake. I mean, that's a simple solution. It's something that's supposed to be done when roads are repaved or resurfaced. Putting in, like they're doing around Culver, these relatively inexpensive catch basin inserts that collect, material. But it doesn't need to be like these really expensive, manufactured treatment devices. We can start small. But I do think that, municipalities, there is the opportunity for lake communities to work with municipalities, and municipalities, are supposed to be, implementing their MS4, programs as part of the compliance with those permits that are issued by the state. I mean, this is nothing new. It's been around now for over a decade. Well,
Thank you so much, Steve. Last year with the 3 HABs forms, we did right after we had to deal with them for the first time in New Jersey on such a level that you shared your expertise. And today with this webinar, we really appreciate your time and expertise and knowledge and dedication. So really, thanks so much for helping us out to get an understanding of this perplexing issue.
Yeah, no, it's a pleasure. I mean, this is, as you can tell, this is a passion for me. It's been a profession, but it's also a passion. And, if other questions come in later on, or, you guys, want to pass something along to me, just shoot me an email. I'm more than happy to, to address any future questions. But thank you for having me this evening. It's a pleasure, working with all of you. And hopefully we can do something to decrease HABs in the state.
Yes, let's hope we can. That about wraps it up for us. Thank you, everybody, for participating. This is the New Jersey Highlands Coalition who presented this. Come to our website, njhighlandscoalition.org. Find out more about us. And we'd love you to become a member. We'd certainly love you to donate. And you'll hear more about us in the upcoming days. Thank you.